So this symbol right here, an element is a member of a set. So this means that 1 is an element in the set of natural numbers. Now, another thing that I see is that 1 is also part of the set of integers. So I write it like that. Now, noticing this, I wonder if there are any other numbers that belong in the set of natural numbers and set of integers. And there are 1, 2, 3, 4, 5, and so on. So that must mean that all the elements in the set of natural numbers are present in the set of integers. So then I say that the set of natural numbers is a subset of the set of integers. This symbol right here denotes that a set is a subset to another set. Okay? Now, for example, I had a set, like, let's name it set A, and it had the elements 1, 2, and 3. And another set, set B, containing the elements 2, 1, and 3. Now, I see that these two sets are equivalent because they have the same elements. Right? They don't necessarily have to be in order. They just have to have the same elements. Now, I see this. I can say that since all the elements in A are present in B, I say that the set of A is a subset of B. Now, using that logic, isn't it true that a set is a subset of itself, right? Because you can say that A is a subset of itself because it contains its own elements. It contains all of its own elements. So this argument makes sense, and this will be a very important thing later. Now let's discuss the set of rational numbers. So the set of rational numbers, denoted by the letter Q, it's a set of numbers that can be represented as A over B. Of course, B cannot equal 0. Alright. So, what are the examples of rational numbers? It's, well, 1/2, its inverse, negative 1/2, 2, 3. So any number that can be expressed as A over B is a rational number. Now, that makes me think the fraction 2 over 1 is equal to 2, right? And we all know that 2 is a natural number. It's also an integer. But any natural number or integer can be represented as a fraction, as 2 over 1. Right? So that must mean that the set of natural number and the set of integers is a subset of the set of rational numbers. Makes sense, right? Now, the set of rational numbers, however, denoted by the letter I, is the set that cannot be represented as A over B, right? Because they have non-repeating and non-terminating decimal representations like pi or square root of 2. Okay? These numbers are irrational, and so we have to extend their definition so that we can perform operations with them, okay? Which will be the topic next time for approximation. Right? So then that makes me think, okay, what's the difference between rational numbers and irrational numbers? Well, they're very different in terms of decimal representation. So that must mean that no number can be both rational and irrational at the same time. Okay? So if no number can be both rational and irrational at the same time, what are their intersections should be? And that's a very important thing right now. So the set that does not contain any element is called the empty set, which is the intersection between the set of rational numbers and irrational numbers. So the empty set, also called the null set, is the set that does not contain any elements because it exists on the overlap of the set of rational and irrational numbers. And in the overlap, no number can exist because of said case. Now, a set is a subset of itself, as we made sense right here. A set is a subset of itself. So that must mean that the empty set can be represented like this itself. It's a subset of itself also. And since it does not contain any elements, it must be a subset of every set. So the empty set is a subset of every set. Okay? It's a subset of any set. Okay? Now we come up with a conclusion that the set of natural numbers and the set is a subset of the set of integers, and the set of integers is a subset of the set of rational numbers. Okay. Now the set of real numbers, the basic definition for real numbers are any number that has a decimal representation 1, 0.5, negative 2, 1 half, pi, square root of 3. So any of these numbers, any actually that belongs in the sets that we've mentioned earlier, they are all real numbers. Real numbers. Now, we've come up with this conclusion, right? Now, since we know that any of these numbers are real numbers and they also belong in different sets, we all know that the set of natural numbers, the set of integers, the set of rational and irrational numbers is a subset of the set of real numbers. Yeah? So we come up with a very, very beautiful conclusion. The set of natural numbers is a subset of the set of integers, and the set of integers is a subset of the set of rational numbers, and the set of rational numbers is a subset of the set of real numbers. Right?